At the very beginning of my encounter of Eastern traditions, I was very threatened myself, for maybe different reasons, but I felt it threatening to leave rational thinking, the analytical mind, the kind of world that I have grown up in and that I have been educated in, and to try and transcend this world in meditative experience. That is something threatening to somebody who does it for the first time. And so many physicists are threatened by the main idea of having their very dear theories compared to mystical traditions.
Fritjof Capra is 46 years old. He studied physics at Vienna University and worked for various institutes in Europe as a theoretical physicist. He now lives in San Francisco. In 1975, Capra wrote a book which made him famous with the general public and unpopular with most of his colleagues. It was called The Tao of Physics. In it, he argued that there exists a profound harmony between the insights of modern physics and Eastern mysticism. He now believes that this unlikely meeting between East and West contains lessons for our global survival. Searching for the fundamental building block of the universe, physicists have divided up matter in experiments that deal with phenomena far beyond the range of the senses. The first candidate for the basic unit of matter was the atom. Later, it was discovered that the atom could be split into smaller component parts, the nucleus and electrons. Then the nucleus itself was found to be divisible into protons and neutrons. But advancing technology added dramatically to the complexity. Over 100 further particles were identified in the wake of numerous experiments with particle accelerators. These instruments consist of vast hollow rings in which bundles of particles are accelerated to almost the speed of light. Other particles can be accelerated in the opposite direction, and the two bundles of subatomic matter made to collide. The results of such a collision can be represented as a graphic display on a computer screen. This is the subatomic world, ruled by the indeterminacy of quantum mechanics. A world in which the search for the simplest particle has led to baffling complexity. A dance of subatomic matter, creating and destroying itself. In trying to understand these phenomena, scientists have had to let go of analogies with the world of the senses. They no longer apply. To grasp the unimaginable, some have turned to ancient symbols used by Eastern mystics. They too contended with the problems of searching for knowledge beyond the senses. One such symbol is the Hindu god Shiva, whose dance represents the creation as an indivisible reality. By contrast, Capra says, classical science has divided nature artificially into separate fragments, and so brought about a state of crisis. The way out lies through an interplay between scientific analysis and mystical intuition.
The global crisis can be seen as essentially a crisis of perception. It comes from the fact that the Cartesian Newtonian worldview is embodied in our social institutions and forms the basis of our approach to the major problems of our time. Now, what are the major problems of our time? Just to take the most urgent ones, the threat of nuclear war, the devastation of the environment, and our inability to deal with hunger around the world. Now, all three of these can be traced back directly to this crisis of perception. that we're using a fragmented, mechanistic, reductionistic worldview to understand and deal with the world around us. What we need is a holistic or ecological worldview which takes into account the fundamental interdependence of all phenomena and activities and the world as a process rather than as a rigid structure.
Capra's book has been translated into 12 languages and almost 1 million copies printed. In calling it the Tao of Physics, he linked his own science with the world of the Chinese philosopher Lao Tzu, the founder of Taoism and a contemporary of Confucius. Tao means way, and in Taoism it is the way or the path along which the universe proceeds. Human fulfillment can only be found in
molecules and atoms, and that these consisted of particles which interacted with one another by creating and destroying other particles. I knew also that the Earth's atmosphere was continually bombarded by showers of cosmic rays. The comparison between physics and mystical traditions is only a small part of a much broader change of worldview and change of consciousness that is now happening in our society. A shift of paradigms, as it is often called. It is a shift from the mechanistic worldview that is expressed in classical physics to a holistic and ecological vision of reality. And this shift is taking place in society. If you wish, it is taking place in the collective unconscious, and people somehow sensed that. So when I wrote the Tao of Physics, I had many enthusiastic reactions from psychologists, from anthropologists, from health professionals, doctors and nurses, from many, many people who felt intuitively that in their fields things were also changing in this direction.
Most of Capra's colleagues have resisted his matchmaking between science and mystical traditions, but he's not the first modern scientist to have made such a connection. That distinction belongs to a Danish physicist whose centenary was celebrated in Copenhagen in October last year, at a symposium attended by 400 leading physicists from all over the world. The institute he founded in 1920 is an international meeting place for physicists. His name was Niels Bohr. Together with other physicists, Niels Bohr opened up the world of subatomic particles, a world in which all sorts of familiar concepts such as location, velocity, mass, and cause and effect were found to lose their established validity. To make sense of such a conceptual upheaval, Bohr turned to other ways of looking at nature. He arrived at a view similar to that of a Hindu, a Taoist, or a Buddhist. He wrote, "If we look for a parallel to the lessons of atomic theory, we must turn to those kinds of epistemological problems with which the Buddha and Lao Tzu have already been confronted." In 1947, Niels Bohr was raised to the Danish peerage. For his coat of arms, he chose the Chinese yin-yang symbol because it embodies a complementary relationship between two opposites. He wanted to express his sense of the harmony between Eastern wisdom and modern physics. But as a young physicist, Bohr had followed his predecessors in trying to bring the description of the atomic world into line with the classical laws of Newtonian physics. In one publication, he illustrated the movement of atomic particles by means of the most popular analogy ever devised for Newtonian motion, billiard balls. Newton was the point of reference for the generations up to the time of Niels Bohr. Technological success, scientific progress, even the understanding of everyday life had grown from his laws. Influenced by his contemporary, the philosopher René Descartes, Newton had compared all moving objects in nature to the movement of cogs in a mechanical clock. Everything that moved was both the cause of a clear-cut effect and the effect of a clear-cut cause. Newton's laws provided people with a sense of security about their place in the universe. They suggested that the universe was a hard fact, independent of the human will. In a similar way, Descartes had made a definite distinction between mind and matter, and saw nature as a vast, mindless machine.
Now, it's quite interesting to go a little deeper into this Cartesian system of thought. When Descartes spoke about a machine, he very specifically meant a clockwork. You see, clocks had reached a high degree of perfection in the 17th century, and all of Europe delighted in mechanical toys, ballerinas, automata. And so Descartes, when Descartes spoke about the human body, for instance, he compared it to a clock. And he said, I compare a healthy man to a well-functioning clock and a sick man to a clock which is not in perfect mechanical condition. And it's very interesting that this metaphor of the clock still dominates modern scientific medicine. You see, when a clock doesn't function, when there's something wrong with a clock, there's usually, or any other kind of machine, there's usually one specific part that is either broken or doesn't work properly. And so the watchmaker will look for that specific part, will interfere and replace it or repair it.
Through the influence of Cartesian thinking, nature, whether living or dead, became unified within a single mechanistic vision of the universe. By understanding the mechanism, it was thought, nothing would be out of reach.
Well, that's an interesting example. NASA, the way NASA put a man on the moon, NASA actually followed exactly the prescription given by Descartes about analytic thinking. You see, the Cartesian method of analytic thinking consists in taking a complex problem and breaking it into pieces solving the pieces and then putting it together again. Now, what did NASA do? They simulated everything in laboratories. They first circled around the Earth, then around the Earth and the Moon, then around the Moon, and then they landed. And those were all distinct steps in the Apollo program.
4 forward, drift into the right a little. Okay.
So, Newtonian physics, or classical science, or in a broader sense, the Cartesian worldview is not wrong. You see, it's limited. It's not wrong. If you build a car, or, you know, a clock, or a sewing machine, or anything, you use implicitly the principles of Newtonian physics. And it's the best physics we have for that domain. But if you go beyond that domain, then, you know, you have to change your models and your theories.
The collapse of the classical worldview began in 1900, when Max Planck proposed that the mechanical energy of an atom came in steps, and when transformed into electromagnetic energy, appeared in little packets, or quanta.
Mesdames, la banque est ouverte.
More imperfections in the Newtonian scheme were revealed by experimental work on the electron, an atomic particle whose behavior refused to be predictable, causing some scientists to compare the order in nature with the probabilities in a game of roulette.
Il ne reviendra plus.
Worse still, electrons appeared only sometimes to be particles. At other times, depending on the way in which you observed them, they seemed to behave like waves or shapes, describing the probability of their being found in a particular place. At the subatomic level, the common sense world of cause and effect no longer applied. The smallest teeth in the cosmic clockwork yielded no more than a probability curve.
And then the next step was to ask, well, what are these probabilities of? And the big surprise was the discovery that there were not probabilities of things, but probabilities of interconnections between things. So a particle for a physicist is not a thing. It's not a small grain of sand or a billiard ball or anything like this. It's an interconnection between things. And then you ask, well, what are these things? And you find out that they are interconnections in turn. And the more you look, the more you find out that, in fact, there are no things at all in the atomic and subatomic world. Reality, physical reality, reveals itself to us in this atomic experiment as a web of interrelations, a web of relationships, a network of interconnected events. And that, I think, was very hard to accept for physicists because they were used to dealing with hard and solid things. In fact, physics, as you know, is called the hard science, or the queen of the hard sciences. And that came from the classical Newtonian image of billiard balls. The world is made of hard and solid objects, the material universe. And now these objects sort of dissipated and dissolved into patterns of probabilities.
One giant of the physics community who argued against a probability interpretation of the universe was Albert Einstein. God does not play dice, he said. But Niels Bohr and other physicists like Max Planck came to embrace such an interpretation. It became known as the quantum theory. In the lecture hall at the Niels Bohr Institute, the revolutionary new theory was the subject of passionate debate. Bohr gathered a circle of brilliant young scientists around himself, the elite of the 20s. Among them was the German physicist Werner Heisenberg, pictured on the right. He pondered the question of whether an atom was an object at all, or just an abstraction of our imagination. In Copenhagen, under Niels Bohr's leadership, the science of physics was acquiring new rules for understanding the natural world. According to Bohr, an atomic particle can only be described in terms of its relationship to the whole. Bohr thus introduced the concept of complementarity. If you're close enough to the individual lines of a drawing to know them in detail, you cannot be removed enough from the drawing as a whole to know what it is, and vice versa. It was found that knowledge of one thing precluded knowledge of another. Heisenberg formulated the uncertainty principle, which states that you can never determine both the position and the velocity of a particle at the same time. This conceptual revolution was expressed in the so-called Copenhagen interpretation of quantum theory, which came to be accepted in 1927. But Einstein was to remain opposed to it right to the end of his life. Niels Bohr was later to say, "He who is not shocked by quantum theory hasn't understood the first thing about it." Heisenberg wrote, "What we observe is not nature itself, but nature exposed to our method of questioning."
No, I think there is a great misunderstanding among the lay public about the meaning of the uncertainty principle. The uncertainty principle does not mean that everything is uncertain. In fact, the original German term Unschärferelation, the fuzziness principle or something like this, fuzziness relation, is much better. What Heisenberg discovered was that classical concepts have only limited validity in the realm of atomic physics, and he determined exactly the range of validity. He found out that there tend to be pairs of concepts. For example, the location of an atom and its velocity. And you can either determine one with complete accuracy or the other, but not both. And the more you know about the location, the position, the fuzzier your information about the velocity will be. The more you measure the velocity, the fuzzier the position will be. So you see, these are the limits of these classical concepts staked out with great precision in a set of mathematical relationships.
The problems of objective observation become clearer if we think of an observer who wants to study a colony of bacteria through a microscope. In order to do so, he has to illuminate the object. But since light consists of particles which interact with the particles of which the bacteria are made, the object of his studies inevitably changes. Or the observer can be compared to an explorer who studies a remote, isolated community, but who influences the people he's studying by his own behavior. And inside particle accelerators, the supermicroscopes of our time, the new rules are a sharp reminder that classical physics has been left behind. As the Copenhagen interpretation says, paradoxically, the observed system is required to be isolated in order to be defined, yet interacting in order to be observed.
You could say, well, why not describe everything in quantum language? Well, you can't, because when you do an experiment, then you say, well, let's do an experiment Friday afternoon, and the whole team will meet at 3 o'clock, and so on. That's classical language, you see. And so you cannot get around the fact that our immediate experience is rooted in classical language, and we have to use that language to do experiments in physics. Yet, the described phenomenon cannot be described in classical language. So that is the paradox. Now, the solution is that the Copenhagen interpretation does not insist on a complete description. The classical apparatus, the instrumentation, is not described completely. And what physicists do is they use a pragmatic approach where they give a set of rules. They say, when you do things in a certain way, in terms of operative descriptions, then somewhere at the end of a long chain of events, you will have a needle, on a scale. And if the needle is between 1 and 3, I will call the experiment positive. If it is above 3, I will call it negative. Something like that, So it's an operational description. The apparatus is described in operational terms. And that is what the Copenhagen interpretation does. Now, if we make a jump now to a mystical tradition, a spiritual tradition, then we see in deep meditative experience, the mystics also say that the observer and the observed fuse. They can no longer be separated, but they go further. They go to a point where there's no distinction, where the entire being dissolves into the universe, and there's no more distinction between you and me and the universe at large. We all have this experience to some extent at certain moments. For instance, in a sexual experience. If you have a really deep sexual experience, there's really no distinction between your lover and yourself. The two fuse, emotionally and physically and spiritually and in every other way. And this is actually a parallel that is often drawn in spiritual traditions, especially in India, the deep sexual experience and the deep mystical experience. But the distinction dissolves, whereas in science the distinction is still there. The separation is no longer there, but the distinction is still there.
Has a more advanced tracking and targeting ability, which allows conventionally armed rockets to destroy a missile's multiple warheads. It could also use advanced technologies such as lasers to destroy multiple warheads as they coast through space. Finally, if any enemy warheads survive the space-borne systems, the ground-based missile defense fires a high-velocity salvo of small projectiles that destroy the warheads at a distance sufficient to protect our Minuteman silos.
The current generation of scientists has grown up with quantum theory. They have not been subjected to the profound shock of discovery experienced by Bohr and his colleagues, nor, on the whole, sought his parallels in the spiritual traditions of the East. And even if quantum physics is in line with mystical traditions, that has not influenced the worldview of modern physicists.
Our Western science, ever since the 17th century, has been obsessed with the notion of control, of man dominating nature. And I use the word man on purpose because it's a patriarchal attitude. And this obsession has led to disaster. It has led to disaster politically when you think about the situation of the third world, the exploitation. You see, exploitation is not very far from control. And so the industrialized world is based on this notion of control and exploitation. And we have pursued this also in science, that in physics, in my own field, we talk about controlled experiments and controlling nature. Now, you see, this is a very profound difference between the worldview of science and the worldview of spiritual traditions. Because in spiritual traditions, and especially in Taoism, to which I am especially attracted, there's no talk about controlling, there's talk about harmonizing with nature, about flowing in the current of the Tao, as the Taoists say, flowing in this reality, about being embedded in the cyclical processes of nature, the sense of embeddedness in larger systems, in the cyclical processes of nature. And I think we have to adopt this attitude of cooperation with nature, and there's no way we can control her. You see, nature is a living environment with whom we have to communicate and cooperate if we want to survive.
The survival of the human race may depend on achieving peaceful coexistence with nature as much as each other, but individual survival is often felt to depend on the conquest of nature. And that means a technology achieved through precise control of the material world. A control based in turn on a precise science. The popular image of mysticism does not include precision as one of its attributes.
Mysticism is often used in science and, especially among physicists, in a way which is very misleading and very wrong. Mysticism is not misty, it's not foggy thinking. It's actually, it goes beyond thinking, of course, but it's not fuzzy at all. It is actually described in opposite terms. You see, when you look at the classical texts of Buddhism or Taoism or Hinduism, a mystical experience is often described as a state of awakening, the clear light, a sword cutting through ignorance. These are the classical, traditional terms that are used. Nothing like fuzzy or vague thinking. Clarity, actually, is always emphasized in a mystical experience. It's a very clear experience, but it's not a rational experience. It goes beyond rational thinking.
There the eye goes not. Speech goes not, nor the mind. We know not, we understand not how one would teach it.
Physicists often say, let's not get into mystical speculations. And so it's used as something bad and to be avoided. Now, if I come along and write a whole book and say, the basic findings of modern physics are in strong agreement with the basic findings of mysticism, that must be very threatening to somebody who believes that this is a vague and fuzzy and highly unscientific activity which should be avoided. And so many physicists have been threatened. And I would say it is the most usual reaction, the most common reaction at first to be threatened.
Man follows the laws of the earth. Earth follows the laws of heaven. Heisenberg. He showed Heisenberg the manuscript of the Tao of Physics and asked him for his reaction.
Well, that was nothing new to him. He said that he had realized that himself. He had also, hinted at it in his books. But he told me something interesting which I have never read anywhere. And that was that he was the guest of Rabindranath Tagore, the famous Indian poet and philosopher, when Heisenberg was in India. And he had long discussions with Tagore about Indian philosophy, about Western science. And Heisenberg told me that these discussions had helped him very much because they had shown him that this new kind of worldview that was emerging from quantum physics was in fact not so crazy. That in fact there was an entire culture, the Indian culture, that was built on the premises of indeterminacy, relativity, interconnectedness, the dynamic nature of the world, the very concepts that emerged from physics. So Heisenberg was well aware of the parallels and very open. And just, to sum it up, he said to me when I closed my manuscript, he said verbatim, basically, I'm in full agreement with you. Now, to me, as an unknown author with a manuscript that was very difficult to sell to a publisher, this was, of course, extremely satisfying, and I left his office very happy, and it gave me a real impetus.
California, a center of both spiritual and scientific frontiersmanship. It's here that Capra has found kindred spirits in the Department of Theoretical Physics of the University of California at Berkeley. In the model being developed there, nature is seen as a finely woven web of interconnected events.
I talked my way on board.
They look really quite hideous. I have a desperate feeling that whatever that creature from the depths that is just...
Taking that limit, there should be
Capra is a guest participant in the group of physicists.
Prime over k prime squared minus k squared minus I0 plus, and that gives you the plus sign for the delta. The plus or the minus depending on which side you approach the branch.
You just indicated that you have some problems with analytic continuation.
No, I have not. I'm saying that I will...
Professor Geoffrey Chew, the leader of this advanced post of theoretical physics, sympathizes with the objections to Capra's stance, but at the same time sees clearly why his bootstrap idea featured prominently in the Tao of physics.
It's difficult to have discipline if the rules are not quite sharp. And if you start introducing mysticism, the rules are not going to be sharp. There are not going to be criteria for evaluating what is first-rate work from what is shoddy work. Now, this tendency to insist on sharp criteria of evaluation can be carried too far, and it often is. But there is value to it. An institution which doesn't insist on high standards generally doesn't accomplish as much as those institutions which are demanding. And to be demanding, you need criteria, you need some kind of rules. I think the feeling is that Capra is proposing that we not worry about rules. And of course, that's what the bootstrap idea is too. So that's right, it's the same thing, you see. So it isn't just Capra who is unpopular. The bootstrap idea generally is not popular in physics for pretty much the same reason.
Your group is an exception, I think, within the University.
Our group is definitely an exception. And within the group, there are different degrees of enthusiasm for the bootstrap idea.
In the 10 years since I wrote the Tao of Physics, I have realized that there's no way that we can adopt Buddhism or Taoism or Hinduism in their original Eastern forms. We have to adapt the essential nature of a spiritual tradition and create our own. And in fact, in Buddhism, this has happened. As Buddhism traveled from India to China to Southeast Asia, Japan, and so on, it was always transformed. Its essence was preserved, but the form was transformed. And I have been very impressed by the insight, really, that our form of spirituality in our modern world may well be something like ecology, in the sense of a profound awareness of the interdependence of all phenomena and the embeddedness of individuals and societies in the cyclical processes of nature. Because everything is an interconnected network. If you are violent to parts of the network, ultimately you are violent to yourself.